Hello. In the last video we talked about kinetic energy. In this video we're going to talk about a different type of energy. We're going to talk about several types, but to give you an example, this picture here, you see that there is a piano. It's being hung up by some sort of rope, maybe a pulley system. How comfortable would you feel sitting or standing beneath that and looking up at it? And the answer would probably be not very comfortable. Well, the question is why? The answer is because it has a type of energy, even though it's not moving, right? Last time we talked about kinetic energy, and I mean, it might be swaying a little, but this piano is not really moving. So why are you afraid of it? You're afraid of it because it has potential energy. You know that it has the potential to unleash a lot of energy due to its position in this case. And so this would specifically be an example of gravitational potential energy. But potential energy is just the energy which is stored in an object. Now, there are different types of potential energy. We'll look at a couple, and then we'll really focus on one type in particular. One is the one that you should probably most, well, you may not be most familiar with. The one you're using right now is chemical potential energy. This is how humans get their energy. There is energy stored up inside of different chemicals and the bonds of different substances. And by altering those substances, by breaking up those bonds, we can release that energy and use it for whatever we need to use it for, whether that's soccer practice or doing our physics homework. And I'll just show you real brief here. For example, glucose. Why does glucose have energy? Well, you see that these all three are actually organic molecules, meaning they're primarily based on carbon, hydrogen, and oxygen. In fact, those are really the only elements that are labeled here. And so in glucose, you have different types of bonds. You see here, these are double bonds, and there's two there. And here you have a single bond. But whenever there is, and they're covalently bonded, meaning they're sharing these electrons. Basically, carbon has 4 electrons that it can share. Hydrogen has 1 electron it can share. And so when you have a hydrogen-carbon bond, they are sharing 2 electrons between the two of them. Basically, they're more stable sharing that than they are individually on their own. When you have a carbon and a hydrogen bond, you see here, it's kind of, I put it in the middle because they share pretty evenly. So the electron's kind of bouncing back and forth. And at any point, it could be found over here, it could be here, it could be here, it could be here. I mean, it's whizzing around very quickly over a fairly large area there that they're sharing. However, when you'll notice that I drew with the oxygen, the electrons are pretty close to the oxygen. And this is because oxygen is an electronegative element, meaning that it kind of holds on to those electrons a bit closer than carbon would. And so when you look at this bond here, you see carbon and oxygen, these electrons are going to tend to stay closer to the oxygen. Now imagine your electron here. You know, what are the chances you're found over here? Not as much, right? You may not be over here. You're probably going to be over here somewhere. And so these electrons are not moving as far as these electrons, which are whizzing around everywhere. And right there, you see that there's a difference in energy. This bond has more energy than this bond. And so when you break up these bonds, when you break up in particular these hydrogen-carbon bonds, that's where you're getting this energy from. When you change it, you're getting energy from those bonds itself. Here you see a saturated fatty acid. These saturated fatty acids are typically those which are very high in calories. For example, butter is a great example. In fact, this kind of shows why butter, this shows why butter is in a solid, because you see all these hydrogen-carbon bonds. It's tons of energy. That's where all your calories are coming from. All of these are hydrogen-carbon bonds all the way down. And also, think about it, if you have another strand of these, another strand of saturated fatty acids, these hydrogens are going to be next to each other, and they can even link up and share these electrons a little bit. And so that's how you get that solid structure that makes butter. Whereas something like this is an unsaturated fatty acid, typically might be found in something like oils, like olive oil or something like that. The difference is they have these double bonds. So they have fewer of these carbon-hydrogen bonds. They're typically lower in calories. And this double bond, it comes at an angle, and so they don't really form this nice structure, and so it's much harder. I mean, imagine trying to build a tower with these. That'd be pretty easy, but a tower with this would be quite tough, and that's why they're not usually in solid form. They're in the liquid form. Again, just something it might be worth knowing. This is how you get your energy. Electrical potential energy. This is probably the one you actually use the most outside of your own body because, well, you have a phone, and that's, your phone is important too. You're using a Chromebook or a computer right now to watch this. I mean, all these things need electricity. And so electrical potential energy is typically found in the form of maybe like a battery or a charged plate. And so what happens is, imagine you have an electron here. Well, on one side of the plates you have a more negative charge. On the other you have a positive charge. Well, what do you think is going to happen to this electron if I place it right here? Well, it's going to be repelled by these positive charges, so it's going to be pushed this way, and it's going to be attracted by these negative. Sorry, I messed that up. Hold on, I can't erase that. So just let's go back. So this is a battery. Imagine I put an electron here, a negatively charged electron. What's going to happen? It's going to be repelled by these negative charges, right? It's going to be pushed this way, and it's going to be attracted by these positive charges. And so it's going to create a moving charge. Well, moving charge is what we call current, which is what you need to move, circuits, and that's what you need to power different objects. So that's how we use electrical potential energy. But the one we're really going to talk about most, and I've got to shift up my box here. Thought I could. Oh well. Is gravitational potential energy. And so you probably want to pause and write this down. This is the type of energy that we will be using, that we'll be talking about most in our equations. And you notice I have an equation here for you. Potential energy is equal to the mass times the acceleration due to gravity times the height. And that's all there is to it. Of course, we're typically going to use 9.8 for G, assuming we're on Earth, but you could figure out your gravitational potential energy on the moon if you wanted to. It would be less because there's less gravitational acceleration on the moon's surface. But gravitational potential energy is stored in an object due to its position in a gravitational field. Again, go back to the piano. You know that piano has a lot of energy stored up inside of it because it has a lot of mass and it's up at a certain height. In gravity, if that string slips or if it gets cut or whatever, gravity is going to pull that down. It's going to turn into a lot of energy that could hurt you, and that's why you don't really want to stand underneath it. Let's do a quick example, although these are pretty straightforward, so I don't think there's much to look at. Whoops, there's the answer. Okay, so see if you can find the answer now. You can just rewind and find it. But here, what's the gravitational potential energy in this scenario? Well, our equation is PE is going to be, potential energy is going to be mgh. And again, it's the same kind of concept, going to be the same. You can even look here. In fact, let's do the units too, just so we can see. Okay, so the mass is 15 kilograms times G is 9.8 meters per second squared times height is in meters. And it's 15 meters. All right, so I'll do the number first. I'll take 15 times 9.8. I get 2,205. But let's look at the unit. Kilogram. You have meter times meter per second squared. Obviously, the meters will come together and make meters squared. So you get kilogram meter squared per second squared. Again, this is the same thing we got last time, that kilogram meter squared per second squared. So you can see that potential energy is the same type of unit as kinetic energy, even though the equation is different, right? The last equation was 1/2 mv squared, but you still get the same unit at the end, which is how you know that they're the same type of unit. Okay, and of course the shortcut is it's 2,205 joules. All right, one more problem. Question is, which one has more potential energy? A 20,000 kilogram truck on top of a 10-meter hill, or a 50 kilogram man in a plane at 5,000 meters? Again, this should be fairly straightforward. It's just mgh. So for A, it's the mass is 20,000 times 9.8, because that's g again, times the height is 10. 20,000 times 9.8 times 10. Okay, it looks like I got 1.96 million joules. But we need to compare it to B. So B is 50 kilograms times 9.8 times the height of 5,000 meters. I multiply that together, I get 2.45 million. So clearly, B has more energy. In fact, it's almost comparable, but B does have more energy, as you might expect. Just because being so high up. But unlike in kinetic, there's one term that got squared. In potential, they're all linear. So there's not one that's more important than the other. Your mass is just as important as your height. Is just as important as the acceleration due to gravity. All right, I'm gonna end the video here. Thanks for watching.